Hey, it looks like it's time to head out to the garage and start grabbing some tools because we're going to use some washers. Right? No nuts, no bolts, just the washers. Right? Because we're going to be looking at the volume of a solid and it's going to be used by cutting it up into washers. Right? Because sometimes we've got two functions, right, instead of one. So here we have like f of x and g of x. And if we think about a real thin rectangle between those two curves, and we decide to give it a spin, right, revolve it around the x-axis, it'll make a washer. Now, of course, if I think about a larger region between those two curves and spin it around that x-axis, we get a three-dimensional shape which has volume. But notice there's a hollow section, right? So it's not like just like a gumdrop. It's kind of more like a thimble or something where you've got the exterior and then you've got a hollow space in between. Of course, in this case, unlike a thimble, the hollow space goes all the way through the top. So let's think about a washer, right? Now, if it was just a flat object, and I think, well, can I find the area? Well, if it was like just a circle, I could certainly find the area, because I know it would just be pi r squared. But if I'm thinking about a washer, yeah, it's a circular shape, but I'm also missing a circle that's been cut out of the inside. So I'd have to subtract the area of the smaller circle that's missing, right? So I got to figure out, okay, what would be the area of the circle, subtract the area of the circle that's missing. And so I'm going to have two different radii, right? I'm going to have the outer radius and I'm going to have the inner radius. So the area is going to be pi times the outer radius squared minus pi times the inner radius squared. And because of the distributive property, we can factor out the pi, which will make it really nice when we get to calculus, because if that's just a constant coefficient, we can actually factor that outside the integration. Now, of course, that's the surface area of the washer. If we're looking at the top surface, right? It's kind of a misnomer because usually when we talk about surface area of a three-dimensional object, we're trying to find the surface of every single side, but in this matter, we're talking about just the surface of one side, like the top side of that washer. But of course, if we want to talk about the volume, well, then we've got to take that surface area and multiply by the thickness. And of course, that thickness is going to be our delta x, or dx. And of course, if I've got some sort of three-dimensional object, instead of slicing this into rectangles or slicing it into circles, we're just going to slice it into a bunch of washers. And of course, if I can find the volume of one of these washers, and find the volume of the next washer, and then find the volume of the next washer, etc., add them all up. Right? So when we do our integration, again, that pi can factor all the way out in front. Right, we go from left to right, so we'll be going from A to B. And then the larger radius squared, subtract the smaller radius squared, will get us like the top surface area of one washer. Multiply by dx, that's the thickness, that gets us the volume of one washer. And then of course when we integrate, we go from A to B. We're adding up all of those volumes. So let's find the volume of a solid of revolution formed by revolving the region bounded above by the graph of f of x equals x And below, by the graph of g of x equals 1 over x, over the interval 1, 4 around the x-axis. So the upper boundary is function f, the lower boundary is function g, right? And so for the region we're talking about from 1 to 4, f of x is the upper function, so that's going to be the larger radius. G of x is the lower function, so that'll be the smaller radius. And for the interval from 1 to 4, that's true, right? If we try to start before 1, we'd notice that, oops, f of x is not the larger function. But it looks like at 1, they are equal to each other. And then from 1 through 4, f of x is definitely the larger one. And then if we think about spinning it, we get a three-dimensional object. And notice that the hollow space does not have like a consistent radius. On the previous diagram, you're like, hey, why don't we just find the volume of what the solid would be and then subtract the volume of the cylinder that's obviously missing inside? Well, here it's not a cylinder inside, right? It's a shape with a varying radius. And so it wouldn't be so simple as to, hey, find the volume of one thing, subtract the volume of the other, because here the radius is constantly changing both for the inner and outer radius. And this is also going to be the last time I got a pretty picture, because I've been stealing off the internet, and for this example I use this, but for the next example you're going to be at the mercy of my limited artistic abilities. Okay, so let's put this thing together. All right, so I need to set up an integral for the volume. So the volume is going to equal, well, let me say, I need pi, right? That pi factored out. Integral from a to b, okay, well, from left to right, we're going to go from 1 to 4. So my integral's got to go from 1 to 4. And then I'm going to need my outer radius squared. Okay, so the one that's further from the x-axis, f of x equals x. So it's x squared. I gotta subtract. And then the inner radius, the smaller radius, well, it'll be g of x. I gotta square that, so 1 over x quantity squared. And of course, then I need my thickness, dx, because we're slicing this thing up. Okay, now before I integrate, what am I even looking at in there? Well, 1 over x times 1 over x is 1 over x squared, right? So that's the only change I made there. Left everything else alone, but I said, okay, 1 times 1 is 1, so that's my numerator. X times x is x squared, that's my denominator. But to integrate this, I really want to see the exponents. So I got to do another little rewrite. I got to recognize that, hey, if I got 1 over x squared, that's really x to the negative 2 power. Now I can see the exponents, so now I can integrate. Right? Got to add 1 to the exponent, divide by the new exponent. So x squared, well, if I add 1 to the exponent, it becomes x to the third. But then I got to divide by 3 because that's the new exponent. The exponent was negative 2. If I add 1, the new exponent is negative 1, but that means I have to divide by negative 1. And of course, we've got to evaluate that at 4. Evaluate it at 1. Subtract those answers. Let me see here. I've got fraction, subtract fraction, but the section fraction is being divided by negative 1. So because I've got a negative and a negative, that's going to come out positive. Right? Subtracting a negative just turns into adding a plain old number. So if you're wondering how come I was able to justify switching that to the positive, it's because we had the negative 1 in the denominator. And before I plug anything in yet, I'm still thinking, that still doesn't look very user-friendly. So let's take that x to negative 1. Let's rewrite it as 1 over x. Now everything looks correct, right? I see x to the third over 3. That looks pretty normal. I see 1 over x. That looks pretty simple. So let's plug in our 4. So I get 4 to the third over 3 plus 1 over 4. We'll figure that out, and then we'll subtract the answer from when we plug in 1. So we get 1 to the third over 3 plus 1 over 1. Of course, 4 to the third power is 64. 1 to the third power is still 1. Now, if you're wondering, no, how come you didn't do something to that 1 over 1? How come you didn't just make that 1 over 1 plain old 1? Well, it looks like I'm going to really need a common denominator. So I thought I'll just leave that as a fraction. So if I see a 3, 4, and 1, I guess my common denominator is going to be a 12. So 64 times 4 got me the 256. 1 times 3 got me a 3. 1 times 4 got me a 4. 12 times 12 got me a 12. All right, so I had to adjust everything to a common denominator. All right, multiplying is so much easier, right? We don't have to worry about a common denominator, but when we add and subtract, we need the common denominators. So it looks like we got 259 over 12 from plugging in the 4. We've got 16 over 12 from plugging in that 1. We subtract and we get 243 over 12. But 243, since 2 plus 4 plus 3 adds up to 9, I know that number is divisible by 9, and therefore it's divisible by 3. So we've actually got 81 times 3 in the numerator. We've got 4 times 3 in the denominator. I can cancel those 3's, and I end up with 81 over 4 pi cubic units. Oh, what a mess that was. Okay, so I've got another example, and I've got it rigged so the computations are easy. Okay, so for this next example, we're not going to have the artistic perfection because I'm not stealing an image off the internet. So the outer radius is just going to be 4 because I've chosen f of x equals 4 to be the upper boundary of the region. Of course, that's just going to be a horizontal line. Through the magic of Desmos, I can get a nice graph of it. G of x equals square root of x. That's going to be the lower boundary of the interval. And then, of course, I want to go from 2 to 4, so I can shade that in and say, okay, that's what the region looks like. But then, of course, I'm going to spin it around the x-axis, right? Do a revolution here. And I'm not going to attempt to do a 3-dimensional rendering. I don't have the kind of software that'll just do that for me, and I'm not going to spend endless hours doing a search engine of the internet to try to get an appropriate figure. So we'll just say, okay, that's what the region looks like before we spin it round and round and round. Of course, once we spin around the x-axis, we'll get a 3-dimensional shape, which will have a volume. So when I set up the integral, again, that pi r squared from the circle, that pi factors all the way out. Because it's a constant, constant coefficient, I can just put it out in front. From left to right, we're going to go from 2 to 4. The outer radius is just going to be plain old 4, so that's 4 squared. When I do radius squared, inner radius is square root of x, of course, because it's, pi r squared, I got to square that. So square root of x squared. 4 squared, of course, is just 16. Square root of x squared, of course, is just x. That integrates quite nicely, right? 16 becomes 16x. When I get to the x, I got to add 1 to the exponent, so it becomes a 2, which means I have to divide by 2. We can plug in the number 4. So I'm going to get 16 times 4 minus 4 squared over 2. I can plug in the number 2, so I'll get 16 times 2 over 2 squared minus 2. course, last time I checked, 16 times 4 is 64. 4 squared is 16. 16 times 2 is 32. And of course, 2 squared is 4. 16 divided by 2 happens to be 8. 4 divided by 2 happens to be 2. I'm like, oh, thank goodness, no fractions. Right? 64 minus 8 will get me a 56. 32 minus 2 is a 30. So finally, I'll take that 56, which is the answer from when I plugged in 4. I'll subtract 30, which was the answer from when we plugged in 2. And 56 minus 30 will give me a 26. So 26 pi is the volume as measured in cubic units. Dun, dun, dun. Alright, so there's a good example that fit onto one page that's not overly messy. The only thing that's lacking is I don't have a good three-dimensional visual, but such is life, right? You can't just steal everything off the internet. Sometimes you gotta do some stuff on your own. I happen to really like the graphics on these letters. And of course, I don't know if that rock stacking craze is still the big thing, but it seems like it used to be when you went out in nature and did some hiking. That was the big thing to do. And those rocks actually probably weigh about, oh, the larger ones I'm guessing might weigh like 50 or 60 pounds. And of course, that sandy beach did not have any rocks, so every one of those rocks had to be hauled down there by hand. And the idea was to try to get the sculpture built in the waves to see if I can get it sturdy enough to survive the waves. But by the time I got all the rocks down there and was done stacking, the tide had gone out so far that the waves were not impacting it. And that was about as tall as I am. So that was kind of close to 5 feet in height. I mean, it wasn't as tall as me, but it was kind of getting up there. And I really would have loved to wait for the tide to come back in and watch the tide knock it over, but it's like I don't have that kind of time. And because it's kind of, well, it's dangerous, right? Imagine if a child came up to that and pushed it, and it was taller than the child and fell on the child, ooh boy. So I had to push it over. And then the next day, there was no evidence of those rocks because as the waves came in and out, the sand shifts around and those rocks just sink right into the sand, and so there was no evidence of that the following day.